Okay, team, we're going to look at the data analysis project part 1. And this is the assignment on Canvas. This assignment will be 50% of your final exam grade. So the final exam is going to be just these 2 data analysis projects. We won't have an actual exam. And it's going to be basically 2 R labs. This project will be following the PDF that I posted here. We'll be using this data set. So UCR Upper Colorado River _runoff.csv. So you can download that. When you download CSV files, it's important to remember, just download it, don't open it. If you open it in Excel or some other spreadsheet document, it's going to change it in a way that will make it hard, or R will not be able to read it using the code examples that I give you. So just download it, don't open it, and then you'll open it in R. Here's the assignment description. Just zoom in a little bit. You're going to turn in a knitted R markdown notebook as before. And here are the prompts. It's important, especially in this final lab assignment, that you narrate what you do and do that outside of code chunks. So that means creating body text, headers and the like to organize. I will be grading a little more closely for formatting and making sure everything kind of looks nice and is easy to read, interpret, and follow. So for the introduction, I'll let you read this. We're going to be using data from the Upper Colorado River Basin. This is stream gauge data. And this Upper Colorado River Basin, hang on, let me show you a picture. Here's the Colorado River Basin. The Upper Colorado one is here outlined in black. And of course, Colorado sits right in the middle of it. Most of the water that is contributed to the Colorado River, which makes its way through the Grand Canyon, through Arizona and California, and eventually to the Gulf of California through Mexico. Most of the water actually comes from Colorado, from our snowmelt. As you can see here, most of the headwaters are in Colorado for the San Juan, the Colorado River, the Yampa. The Green River is mostly in Wyoming. And it's a really important river, obviously, because it sustains life in the West. It allows us to live here in Grand Junction. And the water that passes downstream of Lake Powell, so Lake Powell is right here, Glen Canyon Dam is right here, and this Lee's Ferry is an old ferry area that they crossed the river just before the Grand Canyon started. There's a stream gauge there that the USGS maintains. And at that stream gauge, they measure the river flow every 15 minutes. And that stream gauge is really important because it tells us how much water is being sent downstream from the upper basin. It's this kind of artificial division point to the lower basin. The lower basin, we're required to deliver 7.5 million acre feet of water on average every year to the lower basin. And so it's kind of like this accounting that takes place at the stream gauge at Lee's Ferry. So we're using data based on Lee's Ferry, the stream gauge there. Let me actually show you that gauge. Lee's Ferry gauge, you can see there's this little tower here. That's where they monitor the water level. And they go out on this cable and measure the discharge or velocity of different cross sections every so often to relate the water level or the stage with the discharge. So this is Lee's Ferry. And if you're looking downstream here, you can see this is kind of the start of Marble Canyon and then eventually the Grand Canyon downstream. So it's a cool spot, and that's the gauge. Back to the task at hand, you can read a little bit more background info here in the introduction. We'll be using the Upper Colorado River runoff CSV file, and that file contains 3 columns, the water year. So the water year just refers to the year spanning October 1st to September 31st. So it's not the calendar year, a little bit off. And then we have observed flow. So that is the flow that went past Lee's Ferry each year, and that's a volume in million acre feet. And then we have natural flow, and this is the naturalized flow regime. It's estimated, And the idea is there's a lot of water that's depleted from the upper Colorado River Basin for agriculture, diversions that take the water to the other side of the Continental Divide over to Denver and other places in Wyoming, et cetera. So if you bring all that water and you were to put it back in the Colorado River Basin, the natural flow is what would actually flow past Lee's Ferry without all those depletions. And so it's like the water that's actually generated from the watershed, from all the snow that falls and melts off. So how much water actually would have come out of the basin and entered across Lee's Ferry gauge. So I've got a graph here showing the time series of naturalized flow in blue, observed flow in orange, and then a 10-year moving average of, I believe, naturalized flow. And you can see it's kind of variable. I've got this dashed line for the 7.5 million acre feet, which we have to give. And you can see for the most part, we're above that. But we start to get near that and even dip below it in some cases, which can be challenging. So what we're going to do first for this first part of the project is look at these two data sets, the naturalized flow and observed flow data sets, and fit distributions to them and figure out how well those distributions fit. So that's the bulk of what we're doing. And then once we fit those distributions, I've got a few questions at the end related to probability. So what's the probability that will dip below 7 million acre feet and the like, given the data set or a fitted distribution? So the first thing we'll do is visually compare the two data sets. So I'll have you create box and whisker plots of the two data sets. And you can refer back to lab 3 for the code on how to do that. In lab 3, we did this with some flow data sets and the log normal distribution. In this case, we're just going to do box and whisker plots of the data, so not log transforming or anything like that. So do that, compare them, and also calculate the mean and standard deviation to compare the two data sets, the naturalized and observed flow regimes. Then we'll create a histogram and of the two runoff time series, and we'll overlay what's called a kernel density function. And a kernel density function, I'll just show you right here, is this blue line over the histogram. All it is really a smooth version of the histogram. It has y units of density. So it's like a probability density function, but it's really just based on the data. It's a spline function. It's very similar to when you go to Excel and you want to put a line graph over your data, your XY data, and you choose the smooth plot. And the smooth plot kind of creates these smooth curves through all your data. That's a spline function. It's actually the same kind of math. In this case, we're fitting a smooth curve to a histogram, essentially. So it just kind of gives you a visual representation. It's not an actual specific function that you can point to per se. So we'll plot the spline function, and I give you the code for that. We'll do, first we'll bring our data in right here. So we'll use the read.csv function. If I put the CSV file in the same folder that I'm creating my R markdown file, so just make a folder for this lab, put the R markdown file and the CSV file in there, then all you have to do when you want to pull that in is just use this function read.csv, call that CSV file in quotation marks, and then put it in an object. In this case, I just called it data. So data now is a data frame. Let's jump over to R, and I've got that same code chunk here. I'm using read.csv, and I put that into the data object. And so if I come over here, I can see that data has those 1, 2, 3 columns. The first one is an integer with a year, and the second 2 columns are just numerics because they have decimals, right? If I double click on that data frame, it'll bring it up. And I can just see it just like a spreadsheet here. So each water year starting in 1906, I've got my observed flow and my naturalized flow. The naturalized flow is usually going to be greater than the observed flow. There are some cases where it's not, and I don't really know what's going on there. But for the most part, the naturalized flow will be greater. So I brought that data set in. I'm going to go ahead and pull out the 2 vectors so we can deal with them more easily. I don't want to use the $ each time. So I say data $nat.flow, And so that gives me that particular column, if I use the $sign within this data frame or table. And then I put that into this new vector. So I created two new vectors, nat.flow and observe.flow. I do a histogram. I just give you the example for naturalized flow. Frequency equals false gives me the density values, which is important because I'm going to plot the probability density, kernel density function over that. So histogram, and then I just do lines, and inside that I use the density function for my data set. I gave it a color and a line width, and it'll plot it nicely over that as long as the histogram is in density units. So you'll do that for the observed flow, compare, discuss, right? This is a data analysis project, so I'm going to be looking for some more language narrative from you guys as you interpret the results, interpret the kind of intermediate steps here. So make some observations to make sure you get full credit. The next step we'll do is look for normality. We'll use quantile plots. You can refer back to our lecture on that topic. If that's a little foggy, it's also in your book in the reading sections outlined in Canvas. But we'll be doing QQ plots where we're comparing theoretical quantiles or Z values with the data quantiles and see how linear that is. So here we go. Here's for the naturalized flow regime, a QQ plots. And it looks like it's pretty linear. There's a little bit of divergence on the tails here. I'll ask you to do this for the observed flow. Very basic commands. The first command is QQ norm, put in the data set. This just changes the title of that plot. And then you can add a line using QQ line in the data set. So do that with the observed flow. And then I also ask you to do that with the logs of the observed flow. So if you'll recall, if the logs of something follows a normal distribution, then that particular random variable would be log normally distributed. So you can look at that and use the QQ plot for using that method as well. So do that, and then of course do have some discussion, right? As far as discussion, just a few sentences here. It doesn't have to be super lengthy. But make sure you're kind of tying it back to the theory, what we're learning in class and your readings, and then what you're seeing in the data. The penultimate step, the second to last step, is we'll do maximum likelihood distribution parameter estimation. That's a mouthful. We talked about MLE in class. It's a different method for calculating parameters for a distribution. The normal distribution has two parameters, the mean and standard deviation. As you get other types of distributions, there's more parameters and it becomes more sophisticated. We learned about the method of moments. We've used that where you're relating the mean, standard deviation, and skewness perhaps to parameters for the distribution. You've done that for extreme value distributions as well as other distributions that we've learned in class. The maximum likelihood estimation method is a little more complicated, and we'll just use a function in R to do that. I did post an example of how to do that for an exponential distribution, and that's back in an earlier module if you want to look at the kind of the math for a kind of simplified situation. So we'll use the mass library. This library should come pre-installed in R. But you'll want to call it or kind of load it using the library function, say library mass. Mass is an acronym and is a big textbook on doing stats. And this has a lot of functions in R for doing various stats things. So what we'll do, and I'll kind of just walk through these steps for the maximum likelihood process, is we will use a couple functions here. So the first is the fit distribution function. And what this does, the fit distribution function, is doing the maximum likelihood estimator process. So what you do is you take the function fit distribution, you put in your data set. This is just the vector natural flow. And then you tell it what kind of distribution you want to fit. So you can look at the list of different distributions that you can do with this function by just doing question mark and then fit distribution in the console, and that'll allow you to look at the different examples. So there's normal, log normal. We're going to look at three, those two, and then gamma distribution. It's another kind of skewed distribution that we can fit to data. So using this example, we put in the data set, we say fit the normal distribution, and then we're going to put that into an object. All right, so let's just take a look at what that is in R. So coming over to this same code chunk, I loaded my library mass, and then I did the fit norm. I just added a line here so we can actually look at what happens when we do the fit distribution. So I just said, put it into fit norm, the fit distribution, into this object, and then I did semicolon, and then I typed it again, and that'll print out what's actually contained in fit.norm, this new object we made. So what it gives us is the actual parameter values, the mean and standard deviation, and then it gives us the log likelihood value. So the log likelihood value, it's this negative number, and you'll recall that we do this kind of negative log likelihood method. It's in your textbook as well as in that lecture. That gives us a negative number. And the kind of least negative, if we were to do a bunch of different distributions with maximum likelihood estimators, the least negative log likelihood number, meaning, and we'll look at a bunch of different ones in a minute, that will mean that's the best fit. So the normal distribution for this gives me negative 323. If I fit a log normal distribution and I get negative 316, then I'm going to say that's a little less negative. That is a better fit. Okay, so that's kind of the way we use that metric, as long as it's less negative or closer to zero. All right, now I can do a couple things here. I could just read this out and write it down, right? But I'm gonna just use some functions to extract the values. So I'm gonna take the parameters out. So I'm saying I'm creating a new object called params.norm. I'm using this coefficient function. So coefficient will take out these two coefficient values, the mean and standard deviation. So I say, use the coefficient function on my fit and give me those parameters. So let's do that. Gives me the mean and standard deviation. And then I'm going to extract the log likelihood value. And there it is, the log likelihood value. I just say log like, so that's a capital L for the likelihood, and then to fit.norm. And so it'll extract that actual value. So now I say do that for the log normal and gamma distributions. I ran this code, I kind of hid it from you for the exercise, but you can see that I'm just doing fit distribution, natural flow, log normal in quotation marks, and then gamma in quotation marks, okay? So what you'll do then is you'll just run this same code for the naturalized flow regime, and then for three different distributions, and then the observed flow regime for three different distributions. And then you'll catalog the different log likelihood values as well as the parameters, because then we'll plot those curves over the histogram of the data, and then make an opinion or an educated guess based on the log likelihood values and the visual fit of which distribution you think best fits the data. So what I want you to do then is say, which one do you think, which of the three distributions best fits the naturalized flow and the observed flow, comment on the fit, and then provide a summary table showing your log likelihood values for those three different distributions and two different data sets. That way you can kind of have it all together and then kind of refer to that. Now, the last thing we'll do is just plot everything together. So I've got the histogram in gray, I've got the kernel density function in black, and then I have the three different distributions, normal, log normal, and gamma, with three different colors. So here's the code for that right here. I want you to do this for the observed flow as well, and try to get this to work for naturalized flow using your own code. So what I'm doing here is I'm saying, okay, here is F norms. That's going to be the PDF for the normal distribution. I'm going to use the dnorm function for X. X is just a vector that I made using the sequence function from 0 to 30 by a small interval right here. So here's my vector, and let's go to R to actually look at that. Okay, so here's my X vector, boom, and you can see X over here. It's got a bunch of small values. Then I plug that X vector into the dnorm function, which will spit out a PDF, a probability density function or distribution. I've got to tell it which parameters to use. So for normal, it wants a mean and a standard deviation. I stored those in my parameters function. You can do this however you want, whatever is easier, but I just said, okay, extract the parameters out from the log likelihood fit. And the first one is going to be the mean. So this params norm is just a vector with two data points in it. Okay, so the mean and standard deviation. If I take the first one, that's going to be the mean. The second one is going to be the standard deviation. And then that will give me a new vector with the PDF values in it. So the Y values are density values for a given X. So I'll do that for a log normal and then gamma. Here are the parameters for log normal. So mean log, standard deviation log, and then gamma wants a shape parameter and a rate parameter. And then I use d gamma for that. So you can always check out more of the gamma distribution by doing question mark. I plot my histogram. I label the axes, and then I start adding lines, right? So I do lines, density function, lines, X, and then the 3 different PDFs. And then here's my legend, and I'll let you take a look at how we did the legend. But you can always just copy and paste this. This is just a separate function that comes after a plot. And you've got to give it the names of what you want to show in the legends, the colors, and then line widths associated with that. So you'll recreate this plot for naturalized flow and then also do it for observed flow on your own. All right. Finally, you'll kind of summarize this by saying, okay, here's the goodness of fit metrics, the log likelihood, and here's the histograms with the different plots and the different PDFs fit to it. And I'm going to say that for the naturalized flow, this particular distribution is the best fit. And for the observed flow, this particular distribution is the best fit, and here's why. All right, the last big analysis we'll do before the summary is a chi-square goodness of fit test. So we went over this in class, and I've posted our code walking you through this. So we're just doing the exact same thing here. So I give you R code based on the natural flow. And what I did here, and I'll go back to R to walk you through this, is I said, okay, go back to the data set, and I want to call X the naturalized flow vector, okay? You could do this different ways, but I'm just gonna say, okay, make me a new vector X, put all the naturalized flow in there. So we'll rewrite the old vector X. So now X is just that time series of naturalized flow, okay? And there it is right there, all 100 something values, 113 values. So I'll take the mean, the standard deviation, the length of that vector. I'll do a histogram. And then if you recall from lecture, to do the goodness of fit test, we take the bins for that histogram that equally divides the frequencies up into equal chunks. I count or get the frequency of observations within each bin. And then I get the number of bins. So the chi-squared statistic compares the number of observations I have in each bin. So I call that X sub O, X observations. And then I subtract the expected number of observations in each bin. And that I get from using the normal distribution with the same mean and standard deviation as my data set. So this is the CDF of the normal distribution. So this is how we calculate the chi-squared statistic. We compare that to the critical chi-squared statistic, see if our data statistic is less than, and if it is, then we can say, okay, we can't disprove the null hypothesis at the 0.05 significance level, meaning that in fact the data set is from this distribution. And then you can calculate the p-value. So it's a really basic test. And right now it's set up for the naturalized flow. So all you have to do is go in here and switch out this for the observed flow and run that code again. Make sure you don't have to change anything for X. So everything is based off of X being the data set that you're analyzing. One other thing that you have to change, and this is a big note, and I'll note it right here. When you write note in R, Markdown, it prints in red. So that's to grab your attention. So right here, I'm using the p-norm function, which is the cumulative distribution function for the normal distribution. And so what I'm doing here is I'm saying, okay, is the naturalized flow data set from a normal distribution? Is that sample from a normal distribution, or is it different from a normal distribution? And that's what we're asking with this chi-squared test. I can test any distribution that I want. So if I go to the previous step and I think, well, actually the log normal distribution or the gamma distribution are better fits based on my log likelihood number. Okay, well, I need to switch out this function. And I want to use, instead of p-norm, say it's the gamma distribution, I'm going to use p-gamma. And I'm going to put in X bins again. So I still give it those bin values, right? And then I need to give it the parameters from the data set from the previous step. So for the gamma distribution, it's a shape. Let's look back here at R. But if you go, actually, let's just go to the console and we'll do question mark p gamma. And let's see what it tells us. P gamma, it wants a shape and a rate. And then you give the quantiles, which is going to be those increasing probability values from the bins. So actually, it's not probability values, it's just the actual values of the bins. So shape and rate we can get from coefficients from that log likelihood fit. So that you actually get those parameters from the fit, the log likelihood fit or maximum likelihood estimator fit that you did in the previous part. So what you'll do then is you'll find out whatever function you want to test. You'll use the P version of that, which is the CDF. You'll keep the bins, and then you'll give it the appropriate parameters from your data set as before. So that's the other thing that you'll change. And then you run it as before. So in the end, you'll be able to say, okay, in this case, we tested the normal distribution for the naturalized flow regime. Our chi-squared value from our data set was less than a critical value. So that's true. And our p-value is not very big. So in the end, we can't reject the null hypothesis. We have to say that our data set is from a normal distribution. Okay, and then this is how we report it. Given the relatively small value of chi-squared to the critical chi-squared value, we cannot reject the null hypothesis. Our chi-squared value with 8 degrees of freedom, and the degrees of freedom is calculated up here, is equal to this, and then here's our p-value. So that's how you would report the results. So you'll do that for whatever distribution you want to compare for the naturalized flow and the observed flow. You can just recreate this using the normal distribution for the naturalized flow if you want. But you have to do it on your own for the observed. So finally, analyze and interpret the results. I give you some questions on probability based on the data set and fitted distributions. So I'll let you read those over, and we can also talk about it in class and in office hours. And they give you a code for plotting the empirical cumulative distribution function and the fitted normal distribution. We did that in lab 3 as well. So you'll do that for the naturalized flow and observed runoff series. So that is this first part, and I look forward to talking more about it with you in class and in office hours. Thanks.